Thank you. Thank you for giving me the opportunity. I have some disclaimers, just so that you don't accuse me of wrongful advertisement. What I will present today is correct, but not complete. So be careful if you go around saying things I say. There will be a lot of like asterisks and footnotes that I will not even mention. Also, there will be no punchline. Somehow I'll give you a bunch of facts that make up a funny story in my mind. The funny story helps like pedagogy, like things make kind of sense. What I can tell you is that at the end, I'll give you a list of papers that if you want, after today, you'll be able to read very quickly. If after today you don't want to read those papers, then you don't have to read them. And philosophical questions encouraged at all times. The amount of content is relatively shallow. So not that I'm done in 5 minutes and you want your money back. Okay, and philosophical questions encouraged. Tight moderation also encouraged. We can do peer moderation. If any philosophical debate goes too far away, please, anyone feel free to stop it. Cool. Now, yes. So this funny story I call the quantum kernel saga. There is like the three main steps are there is reason to believe there's some relation between QML and kernel methods. And then these are like oversimplified statements from papers, kind of. So it's kind of funny. Before that, we'll have like a part 0 with kind of preliminaries. And part 4 is this list of papers that are related, important, interesting, and you'll be well equipped to read afterwards if you still want it. Okay. Now, first, so maybe you were recently in the group meeting where I had my mini talk where I made this whole point of being strict about supervised learning, machine learning. I will not make strict points now, just fixing notation for us to speak about different things. We will have a d-dimensional real data domain. And we will have binary labels. So we'll talk about learning tasks where we're given a bunch of vectors, and to each vector we associate either +1 or -1. And our goal is to come up with a labeling function somehow. So it's a simple case. And as I said the other day, I model a learning task via a distribution over the domain and the codomain. This is very general. If you don't like this, you can also think of this as there is some distribution over X and then a deterministic function over Y. This is just because some people have strong opinions about this. If you don't have strong opinions, just a distribution. So the goal will be doing like classification, supervised learning. We'll be given a bunch of labeled examples, and from those we need to infer the rest. These labeled examples we call the training set that I write like this. And we assume they are D from the distribution. And if you remember, there's this like this kind of idea we're trying to follow that somehow we want to learn the truth from a small set of examples. The other time I presented this, I didn't go much deeper than this, but today we will be talking about like loss functions and stuff. So I also introduce those things. When I talk about a loss function, formally speaking, it's just some measure of distance over the label space. This is more general. For binary classification, you don't need to define it this way, but it's good for me. So I'll just write it this way. Yes, so just whatever measure of distance or measure of this similarity. For us, we will say that the distance is just like the coming distance. So if they are the same, distance 0. If they are not the same, distance 1, which is a Hamming distance for single bits. And yes,
sorry, so this y just contains a +1 and -1.
Yeah.
Right.
1 second.
Okay.
Okay. I define this in general.
Sure.
This becomes a bit more relevant once we remember what we're doing, and what we're doing is trying to solve a classification problem. For that, we'll consider a family of functions, a set of functions. This notation means all functions from x to y. And so our machine learning model will be associated with, like, our machine learning model will give rise to one set of functions. And we'll be trying to find good functions within this set. And for that, we define, you will see, a risk function. It depends on the distribution, and takes as input a function, which will be the loss function in expectation over the distribution for our prediction and the correct label. So in this equation, we have an expectation over input-output pairs. What we do is we kind of sample. You can think of this as an oracle. We sample from this oracle. It gives us x and y. We give x to our model, and that returns a target label. And then we compare the label we got from the label we got from the label from the model and the true label from the oracle. And then if this is high, that's bad. If this is low, it's good. All of this is a bit too general for the simple case of binary classification, but it's still good to have seen it once.
Right. Okay, but so just to get the idea right, like x is your, like, where your data, you can classify pictures or whatever.
Yes, lowercase x would be one picture.
Right, yeah, and uppercase x is the set of all?
Uppercase x is the domain, yes, the set of all pictures, yes.
Okay, and then what the function does, or what we want the function to map x, something in x to the correct label.
Yes.
Like there's a correct classification, and we want our function to see this correct classification.
Yes.
Yeah, okay.
In all generality, we don't even need to assume that there is a correct. We just need to assume that there's some measure of quality. Like there doesn't need to be a perfect solution. If it's there, perfect. Okay. We don't require it ahead of time.
For sure. Okay.
Our goal would just be to find good solutions.
Okay. No, just so like, you know what x and y.
Yeah. So start. Very good. If you open a machine learning demo on the internet because you want to learn machine learning, classical machine learning, one step will be downloading data from the internet. You go to something called MNIST or CIFAR or ImageNet, and that will give you a set, like it's uppercase S, which will be a collection of inputs. The inputs will be images, and outputs will be labeled cat, dog, boat, whatever. Next to that, you will download some neural network model that people have invented, and that will come with a training algorithm, and somehow magic will happen. And based on the training data that you used, this whole model will result in one function. And what this one function is supposed to do is, if now we generate a new data, or we get a new image from cats and dogs, and we give it to this function, that function will say, well, this is a cat. And from the definitions, like, correctness is not part of the definitions. Ideally, we do it in a way that it says it's a cat when it's a cat, but this is the framework to talk about it.
And it's always the case, I guess, that for this R to be relevant, right? In the cases that
this R is relevant with some asterisk, but go ahead.
Yeah, so for that to make sense to be relevant for me, there is the assumption. And my question is if this is universal in the field, like somehow you will question, you are interested in the error that you make once the questions that you ask are distributed according to your training data, not this D. So I care.
Very good. 1 second. So we call this the expected risk. And our goal in life is to find lowercase f such the expected risk is small. This is a problem we want to solve. But one thing I didn't tell you, should have told you, we always standardly consider D to be a known. So we don't assume we have access to D as a distribution.
Good. This unknown, but somehow the game is that the question. So once I learned something about regarding with this S, but then I will build an approximation of this F, and I want this approximation to be good once I input new X that are distributed according to the same.
So the distribution is always the same. Is that what
Both
yes.
For the training and also then when I will benchmark it,
yes,
because
exactly.
if I train this distribution, but then I ask always the same, then this loss doesn't tell me anything.
Yes. So this is what. Yeah. Okay. I didn't write this down. I assume there is one distribution, time independent, always the same distribution.
Always like this. How in this?
Some people study out of distribution learning also. So if you can think of it, someone has formalized it, but I will ignore that possibility. So for me, the distribution is always the same. And from the point of view of studying this, if you break this assumption, then immediately there are much fewer things you can even say. So you can formalize it, it's less fruitful, I guess. So I would say that exists, but ignore, delete it from your hard drive for the purposes of this talk. But yeah, so one thing Jose said was the questions we can ask. And as we say, the distribution is fixed, is unknown, so we cannot ask questions about the distribution. Instead, we have to ask questions about the samples we have been given from the distribution, which I call uppercase S. And the main thing you would talk about is this. If you look at it, it's quite similar to the expected risk. Just it's an expectation value over the uniform distribution over S, or it's like a finite sample expectation value. This we call the empirical risk. You also call it the training error. That's what you call it. So one thing I said in the presentation in the group meeting was, in supervised learning, there are two problems: the problem we want to solve and the problem we can solve. The expected risk is the problem we want to solve. Find something that gives a low expected risk. The empirical risk is the problem we can solve, because we have access to S, we have access to F. In principle, we have the ingredients to solve it. And this is how we go about it. Now, last time I said more things about this, but this time I don't need it because I will not be talking about deep questions. Instead, the last ingredient I need is a notion of learning algorithm. Learning algorithm is something that takes as input data, looks through our function family, KDF, and picks one function among the family. So take as input the training set. I define it this way because if you fix the size, then things get weird. Like this should be the union of all possible sizes of all possible training sets, which is annoying. That's why I use this weird thing. And so in goes the training set, out goes a single function. The single function is the output of the signal. There could be randomization inside the algorithm. Like everything is allowed, but we use just capital A to talk about it. Cool. This is the zeros preliminaries. Does this make sense? Awesome.
So the input to the algorithm, or the domain of the algorithm, is basically the power set of
Yes.
The unknown distribution.
Correct.
Okay.
Yes, but when I say that thing, people come at me with pitchforks. So I learned not to say.
Sure.
Okay. Then for number one, instead of triggering your sense of smell, let me rephrase the title of number one. It's from linear regression to cure. Hopefully, you're all super familiar with linear regression. Linear regression is home, and QML is Ithaca. So we go. Yes. So the way I will talk about this is similar to more references. One from this house. And the other one almost from this house. The other one is Sophia. Okay, let's see the easy example. In all of this, we have a two-dimensional problem. So there's x1, x2, and we are given training data that looks like this. Right, this is S. I guess it doesn't look green, but this is green, this is blue. We say green is +1, blue is -1. We look at this and we immediately say, whoa, this problem looks linearly separable, meaning there should be a linear function of these two variables that separates the +1 from the -1. Because it looks linearly separable, we, the smart people, say, okay, then the machine learning model will be linear functions. Linear functions are characterized by a vector. And let's not say that this is two-dimensional, let's pretend this is d-dimensional. This is just like the picture. But we're given data, d-dimensional, to be consistent. We believe it's linearly separable. We restrict ourselves to linear models. And once we do this, there's one thing that
don't you need an offset vector?
let's not have it. Let's pad x with one, with a single. You could have it, yes, it's fine. Cool.
And what for?
Just in case, because this is things that go through the origin.
Because you are already thinking that this. Well, yes, yeah.
Yes, yeah, you should. Good. I mean, said otherwise, machine learning people are smarter than me, and when they're given training data, they always recenter and rescale it.
Or usually we can just add auxiliary variable to extend only. So they
Yes,
Yeah, I'll draw them there and here. No?
you can do all of those things. Let's imagine that we took care of all of these things. Okay, once we do this, I defined my loss functions in terms of f, but it's common once you have a function family that's parameterized by some values to rewrite it in terms of those parameters. Like, this is just things that people do. Now, if we have those things, there are two things we can do, at least. First thing we could do is, let's get a random vector. This means Gaussian random dimension. And let's do gradient. On the empirical risk. And that will result on some vector. It's a bit abstract, but yes.
Like right now, our task is to find best vector given some training set or
Our task is to find the best omega to minimize this,
yeah.
but we cannot compute this, we can compute that. So we want to find the best omega.
Sure. Okay.
To find this.
Sure.
This is one thing we could. It's what's trendy in machine learning, I guess. And now, opinion gauge. If you had to actually solve this problem, can you raise your hand if this is what you would have done?
I don't know what gradient descent is. Jeff.
But it's initialized at random, compute this function, and compute the gradient.
Does that include stochastic gradient descent?
Yeah. So, how do I write this best? So, this is omega 0. Then we have an iteration for t from 1 to big T. This is a hyperparameter that you fix. You do omega t plus 1, omega t plus, what's the word? What symbol is with it? Psi? No, that's the step, eta. You compute the gradient of the empirical risk with respect to your parameters, and you have an iterative, and you have an update rule based on this. You start somewhere random, you take the grade, and you move against the gradient because you want to find minimum. You do this until convergence, or until you get tired, or until people tell you to, and then you output the last one, or you can also then keep all of this in memory, go back, check which one was the best, because sometimes for messy functions, if your gradient has only finite precision, weird things can happen. So you can improve this however you would like, but the idea, you do this a bunch of times, and you output the best thing you have. That's more than gradient descent. Like, when I say gradient descent, I mean all possible local optimization iterative methods. This is just a representative example. At the end, we would have one. Now that we're all on the same page, raise your hand if this is what you would have done to solve that problem. We have 3 hands, awesome. 4 hands. Raise your hand if you have a better way to.
So
You raise hands on both sides.
like it's a linear problem, so you can literally compute analytically.
Perfect. Thank you. What I call option 2. Yeah. Yes, it does, but let's ignore that. I forgot. I wanted to do this gimmick of bringing a book and wrap it and say linear optimization. And like, so just tell you read a linear optimization book. That's what you should do. That's option 2. Sorry. And what the relevant thing that a linear optimization book would tell you is that it's enough for you to consider not all possible linear functions, but a subset of linear functions that depends on your training data. In particular, find functions of this form. This may come as a surprise to you, but this is a way to rewrite the typical things you read about Lagrange multipliers and using the information you have. And so if you write down the problem of optimizing this function and you do cool, smart stuff from linear optimization, you know that the solution is of this form. So you reduce the problem of finding the best linear fit to finding this alpha parameters. And one thing that is cool and will be relevant later is we started from something whose dimension depends on t. Now we have something whose dimension depends on n. So potentially this opens the door for interesting behavior to happen at the kind of at the difference between one side and the other. Of course, this is still a linear model because this is equivalent to say omega equals this thing because the inner product is bilinear, so we're all fine. And another thing we know from linear optimization is that to find the optimal alpha, we only need to compute all the inner products from the data we're given. So there are two different pieces of information. One, we only need functions of this form. And two, we have a deterministic, convex, bounded, a very good optimization problem that we know how to solve deterministically, which fixes the optimal alphas. And the only thing it needs is evaluation of the inner products. These inner products we usually mount in a matrix, and we call it the Gram matrix. This is cool. And if we did these things, like if we did option 1 versus option 2, we would potentially find two different solutions. In principle, like nothing guarantees that those would give the same answer, and that's fine. Right? Sorry. I had a subtitle. I forgot to add the subtitle. The subtitle was linear optimization.
Well, it would kind of taking away the whole game.
Yes, you're right. That was on purpose. And now we have 1.2, which I guess also takes the whole game, which is carry my iPad with me, which is okay. Yes, it does take over the game. Linear optimization under the hood. Cool. Similar situation as before. We're given some data set. And I will not do colors because it doesn't help that much. The data set looks like this. Crosses are +1, circles are -1. Now, it might not be obvious, but this is not linear acceptable. Which means you can try to find like a linear cut, but you will always leave some stuff out. Does that mean this is a difficult optimization problem? Potentially no, for potentially different reasons. But there's one thing we could do, we're trying to do, which is inflate, meaning take your d dimensions and somehow make it more. Take your d-dimensional vectors and inflate them to some higher dimensional space. In particular, we could imagine that there exists a known map that for this data results in something of this form. This could happen. Like you could plant a parabol in here, centered, and say that the third dimension is the height or something like this. You could do that. Doing that would amount to considering the set of linear functions on the new domain where we are mapping our data. And if we did this, then we see that these linear functions are still specified by a single vector, but this vector now doesn't have the dimensions of the original data. Now it has the dimensions of our target space, whatever that is. Now, if we agree that this is something we could do, again, we could go about trying to find the best parameters the same way as before, either by a gradient descent and in principle, okay, let me have more specific. Same as before, we could consider just doing gradient descent on this new space. Doing this in principle, unless something weird happens, should take us time scaling at least in the dimension of the target space, because writing down value like omega once takes us time. So whatever we do should not be faster than d in principle. And we could also again do the other option, which in this case would be considering functions on this new domain of, that depend on the training data. Again, parameterized by these alphas. And we inherit the same guarantees as before. Linear optimization tells us that this is the optimal, and it's a form of the optimal of this problem. And it tells us that we only need to evaluate inner products of our data in order to find the optimal. So same thing as before, this returns some optimal parameters. And from this naive approach of just counting the dimension of the optimization problem we're running, the runtime of this thing would not necessarily scale with the dimension of the space, but rather it would scale with the number of data we have. This opens the door for us doing cool stuff on very high dimensional spaces if the amount of data we have is not that big. And say this linear, I call this linear optimization under the hood because in the end, we set up a linear optimization problem, like finding the optimal linear model. But we found something where we had a linear model on a new space where we mapped our data. On our original space, we did non-linear classification. So this is a pretty powerful idea. The optimization problem on the original space would have been non-convex, non-anything good, and we still found a good solution by mapping it to a space where the optimization convex was linear and bounded and good and everything we want. And if we think of it from the point of view of the original space, we've achieved non-linear classification without the good guarantees of linear classification. So this is kind of one of the big ideas of machine learning in general. And this is really cool. So linear in RP, non-linear in X.
So maybe this is a pedantic question beside the point of what you're trying to make, but like the hyperplane you find in bigger space, there's like in general there's no guarantee that there's a pre-image under 5, right? Like 5 to the minus 1, quote unquote, might not make sense on the whole hyperplane. Does it matter? Should I just ignore it?
I think it doesn't matter. That means that I'm technically not allowed to paint this picture of the pre-image.
Right.
But that's just a moral story. Like in the end, I will never use it.
Okay, yeah, that's
Can I also ask a question? Sorry.
Yes.
Considering the fact that Spanum is mentally impolite as a backup reason for this.
Yes.
Can I ask a strange question?
Mhm.
Because, we have thought of aware of this idea and so on, but can you maybe elaborate a little bit to what extent that idea is related to the hierarchies of convex outer approximations or relaxations?
I cannot comment.
Polynomial problems, right? I mean, these are nonlinear problems.
Yeah.
And
Yeah, and
in an optimization problem, you can always optimize over a linear function subject to a polynomial constraint. That the set is funny, that nonlinear is related.
Yeah.
And the objective function is linear.
yeah,
Now
yeah.
say, okay, great, and I just replace my funny wobbly set by the convex hull, and I have it. And since it's a linear function anyway, the convex hull will be the same objective value.
Yeah.
The problem computing the convex hull is convex relaxation techniques do is they embed this in hierarchies of larger and larger spaces, so that the projection of the old variables provide better and better outer approximations of this funny convex hull in the original set. In
Yeah.
a way, it seems morally quite
Yeah.
good because I mean it's a wobbly set, and then you go to big spaces to then look at projections into the old ones. And somehow I know both literatures reasonably well.
Yeah.
I've never seen them connected. And I wonder whether this is a cultural problem or whether I just don't get it. And Daniel maybe not.
Is that,
I don't know, but,
is that another question or a reply?
comment. I don't know. Maybe you do it.
Then let me just reply. Yes. I agree with everything you said. I'm not aware of any relation. I think that properties that get exploited are different. Like here, I think what you.
Okay, I think I get it. Can I answer myself and then you say yes, no?
Mhm.
Because it's slightly different. In one sense, the optimization problem, you're looking at the optimal objective value of one function, whereas in the other setting, you look at separation of entire sets. So that task is quite different.
That's not how I think about it, but I can see how that answers it for you, if that makes sense. Yeah, I think in the end, they're like properties we want of the problem and that we want to exploit because we assume we have access to that information. And I presume this is where these things differ, even though I fully see that the morals are very close. I had never thought of it though.
Okay.
So maybe the literature exists and I don't know.
For the kernel methods, you don't need complexity.
Who has mentioned kernel methods? There have no kernels.
Complexity presented.
The linear optimization under the hood. Yeah. Okay.
Right, so you drew it that one of the sets is convex. Okay, but you could have drawn it in.
Yes. So one thing I haven't said, and I will not say, and you should be mad that I will not say, is okay. This is a funny example, but in general, if I give you a banana, can you guarantee that you'll know how to find an inflation that will result in linear separation? And the answer is no in general, and I will not even give you any idea about how to do it in practice. So from now on, I pretend that I'm so smart that I always know this inflation. Sorry, but
And different inflations give you different.
yes. Different inflations result in different spaces, and in the different spaces, like different spaces would all come with like a deterministic solution, convex optimization problem. But when you map them back, they could result in different things. Yes,
Sorry, but it finishes.
I was going to say something.
Okay, I just want to ask why do you still keep the two options? Is there a reason why?
Yes, there's a
Okay.
reason. It's coming. One thing is, I made a point of writing this one times, and I made a point of saying that I was being deliberately naive. Of course, here I'm saying the runtime of option 2 could depend only on big N and not on big P. But to value the function, I need to compute a p-dimensional inner product. So how will the p-dimensional inner product not scale as p? And this is very important. This is relevant or interesting when when somehow something's going on that allows me to evaluate this function fast and cheap and independently, which is a strong structure. But the good thing is that this happens commonly. Said otherwise, we only use this machinery on those instances where we do the inflation with a bunch of things, but computing this inner product is much cheaper than writing down the inflated vector. And this is super, super, super important. Maybe I got ahead of myself. Sorry, 1.3. I will not change anything. I will just give things names, and from now on, certain words will stop being taboo.
Sorry, yes, one. I'd like to answer my own comment about the pre-image. Like phi is some continuous function. I probably
Doesn't need
or
to
whatever.
It doesn't need to be anything.
Okay,
If it were, then
right. Yeah, if it were continuous, then of course, like the image is path connected, right? So the hyperplane will intersect something between
Yes.
the sets. Then will get a
yeah. So I think
something. Yeah,
at least by implicit definition, it in practice it would help.
sure. Yeah,
But not in alternative because I didn't impose any nice properties.
yeah. No, that's fine. Still, I retract my previous question.
Okay. So phi from now on, we call the feature map. I replace RP with H. H is a Hilbert space. Which we call feature space. Which means it comes with an inner product. And then the $1 million word. I will use K. To talk about the kernel. The kernel, the function of the variables, it just shorthand for saying the inner product of feature vectors, which might not be the full inner product because there might be parts of H that are not in the image of phi. So the definition is defined, but this is what it is. And when I talk about kernel methods, generically, I'll mean that I look at function families of this one. Where I haven't changed anything important, I've just given notation and given names to things. It's not very important, but like this is kind of a bottom-up definition. Given a feature map, its inner product is a kernel function, but you can also define kernel functions independently of feature maps, and that's like a super annoying definition. Kernel function is a function of two variables, which is symmetric under exchange and is positive semi-definite. What does it mean for a function to be positive semi-definite? It means that I give you any set of data, any set of any number of x's, then you build a matrix, the ground matrix. The K is the kernel matrix also. It's positive semi-definite for all Xn for all n. So it's like an infinite dimensional version of positive semi-definite matrices. I have never checked, but I assume this is undecidable in general. So it's not a very useful property. I give you a random function. Your best bet at checking whether it's positive semi-definite is either try random x's until you find a matrix that is not positive semi-definite, or look at it hard enough until you can express it as an inner product. Once you can express it as an inner product, you win. That is a kernel function.
In a sense, with analog of complete positivity, right? Like if I think of the x as a segment into a big vector, then
I think it's just positive definiteness. There's no second in, I think. Maybe
no, sure. Like if you take the x's and you step them into a big vector.
Yes.
And then you take the inner product of the big matrix and the blocks. They should be these k xi x1.
I believe you. I have never seen it this way, but I mean, if it's true, you would know. So I take your authority argument.
But regardless of whether it's true or not, this connection to complete positivity, it won't be relevant anyway.
Not that.
Or what you were talking about.
Not for.
Okay.
Not yet. No. Okay. Sorry. We're almost at the quantum. Which makes me realize I made sure to try to not go over 10, and I cannot promise that I was finally enough. Okay, I had an example of a kernel function that has this property of evaluating the kernel being independent of the dimension of the Hilbert space. I was going to leave it as an exercise for the reader, so I will not even write it down. I will just say it. That if you take two vectors, x prime, and you define a kernel function as the exponential of their norm negative, like e to the minus x prime norm squared, then that thing is a kernel function on an infinite dimensional feature space. So if the complexity of evaluating that went with the dimension of the feature space, it would have infinite dimension, infinite runtime, but it doesn't. It's linear in D. So find the inner product representation of this Gaussian function as an instance. Okay. We've done all the classical part. Now, just for the purpose of adding names, consider quantum feature maps, where the Hilbert space we will consider is the set of Hermitian operators of n qubits. In my head, I will use n and d interchangeably, but lowercase n is number of qubits, d is dimension. They don't need to be exactly equal, doesn't matter. Then the quantum feature map is just the parameterized quantum state. This is very abstract, and usually people don't like it when I write this. So imagine you have a set of unitary matrices, in principle, set of quantum circuits that you can implement that depend on X. Then one common way of defining the quantum feature map is as the state preparation circuit of that unitary. You write it this way, it opens up different ways of thinking about it. This is exactly how we talk about parameters quantum circuits. So X could be the arguments that go into a parameters quantum circuit. This is a bit different from what people usually do, but imagine you set up a parameters quantum circuit whose number of parameters is equal to the number of pixels in images. And then you set the values of those parameters as the pixel values. Not what you usually do, but this is kind of the mindset for QML. You write it this way, you can also think of like BQP type things, where you have like uniform complexity, meaning this is the circuit that evaluates the BQP hard function, then it's indexed by some bit strings. The same formalism applies to both. And then when we do this, we concentrate on linear models on quantum feature space. Feature space. are functions of this form. Because on the Hilbert space of Hermitian matrices, the canonical inner product is the Hilbert inner product, which is this. And I write it this way because now it's clear that this is an expectation value of something that we could evaluate on a quantum computer. M is some observable, some Hamiltonian, that in principle you can measure. Then one way of giving rise to functions, of generating functions, is this way. And if you generate functions this way, you have committed to a single parameterized unitary, so like the feature map is fixed. And this is just the set of all linear functions of this feature map, if that makes sense. This justifies why we talk about density matrices and not Katz and Brass, because it's not immediately clear that we can evaluate linear functions of Katz and Brass, whereas it's immediately clear that we can evaluate linear functions of density matrices. And that's helpful for us.
All right, so to be clear, what previously was our phi, now is our
Rho, yes.
yeah.
Sorry, in my notes I wrote it with more steps, but I want to speed up. But
No, and x is x as before. No,
Yes.
This is the
Yes.
variables that you want to classify,
yes.
and
Okay, so this is where phi is rho, h is Hermitian, and this inner product is the Hilbert.
okay. I think what confused me is when you wrote the quantum feature map that I got the impression that x belongs to h. No, this is
No.
This okay.
I haven't changed the data domain.
Good.
And I could do things in a way to guarantee that this inner product is always +1 or -1, for the purposes of also not changing the label domain. So in principle, this should build naturally on top of the previous things we said. This seems very simple, but this is the crux of quantum machine learning. It's take this and try to be smart about it. And in trying to be smart about it, there's one immediate first limitation, which is that we have too many variables. We cannot write down uppercase M for most M's. I phrase it as a limitation because it makes my life difficult in coming up with smart ways of exploring large classes of capital M. If this was a funding meeting, I would say this is the potential advantage for quantum machine learning. We have access to an exponentially large feature space that we wouldn't have access to otherwise. So quantum machine learning is, let's do linear stuff on quantum feature space, because we can with a quantum computer. And the reason why I was talking about two options the whole time is because this is a problem, we need to do something about it. And there are two things we typically do about it. We either consider parameterized observables, and they are parameterized via an efficient amount of parameters, which is what we do in PQCs. So somehow we could have a PQC that's in charge of encoding the data, and a PQC that's in charge of parameterizing this super large space. If we do this, then the machine learning model we're considering is functions of theta
So each theta is a candidate.
Correct. That's exactly what I was going to. And to keep notation consistent, let's say we have P many parameters. Now, there's our function family. Rho is fixed for every different theta in this domain. We have a different observable. And this is a bit like option one. This is something with which we can do grain descent. We can, in principle, initialize this at random, initialize the thetas at random, then consider the empirical risk, come up with ways of computing gradients, which we have, and then just do gradient descent.
Sorry, Elias, what is here now the training data? The raw,
Same as before. I haven't changed the
X.
problem hasn't changed. It's just how we solve
So
it.
I just imagine like given a bunch of X,
Yes,
and for each X there is a row.
yes. I should not have deleted the 0 part. I'm sorry. Yes,
And then here the optimization means try different theta such that
you can
this-
try a classical optimization algorithm with access to these functions, which will try a bunch of different thetas with some logic to it, and we choose a good one, and we'll output that. And from then on, whenever I'm giving you a new cat, a new image, you will turn on your computer, put the X on the feature map, check which parameters your algorithm outputted, put those in, run it a bunch of times, get an expectation value, and say this is a cat or a dog based on whether you observe +1s or -1s.
Yeah. Alright.
Opinion gauge. Who was aware that this is what we do in QML? Raise your hand. More or less. Okay, raise your hand if you think we were doing smarter things. Good. All of you just got it, all of us dumb, actually. We're doing dumber things. You said we're doing dumber things than this. Okay, that's option one. Option two, which is why we're here today, is lo and behold, quantum kernels. And of course, now everything clicks. You have a eureka moment. You know exactly what I'll write before writing it down. But if we do quantum kernel method, which is the read a linear optimization book approach, you say, okay, we have our classical data. We map it to a quantum state. Then what linear optimization tells us is that the only thing we need to do is consider inner products of the data we're given. Right? Assuming that I can compute these inner products, what I could do is just consider functions of this form, which I can write differently. So if you prefer it, I'm not stealing your money. This is still a linear model on the feature space, on the quantum feature space. And this part is then the quantum kernel.
So instead of checking all possible M's, it's enough to check the span of your training.
Precisely.
Okay.
Yes. And okay, we had option one, option two. We look at it, and again, in this naive approach, the runtime of option one would go as P, number of parameters. Runtime of option two would go as capital N, number of data. This is not earth-shattering, just reminding. In principle, P is freely choosable. You can do whatever you want. if you take p to the exponential, then you're suddenly recovering the entire space. And then this stops being a limitation. And on this limit of exponentially many training data or exponentially many parameters, you see that those things end up covering each other. Okay, this is the end of 1. 2 and 3 were just one section each, so like they're super short. But would you like to stop, or should I keep going?
No, I feel like for what's worth, I would say it's like 25 minutes.
Okay. If anyone wants to leave starting now, I will not hold it against you. Okay, sorry. Bombastic. We finished point number 1. Questions? Philosophical questions. Yes.
So we would compute the kernel on the quantum computer. We would compute kx x prime for all.
Yeah. So, yes, 3 things. 1, linear optimization tells us this is good. 2, linear optimization also tells us that to find the optimal alphas, only thing we have to do is compute the kernel of our input data. So we need to run the quantum algorithm quadratically many times to estimate all of these inner products. From that we get alpha. And then we're very happy. We're very happy until tomorrow when someone comes and gives you another image. Because now, in this case, if you want to produce a value for this new image, you just need to run the computer once. You only need to produce one expectation value. Whereas in this case, you need to run it again for all training data, which is not the end of the world, but it's constant versus linear. There's room for complaint. But operationally, this is what it would look like.
And the alphas we store.
Yes. Yes. If you want to forget that this comes from classical information, if you want to set up a binary classification problem on quantum states, whatever that means, then you have a bit of a problem because the training data quantum states, you have to use them during training, but you also need to store them for tomorrow. And this poses some problems or talking about this for quantum data because you need to hold arbitrarily many quantum states for arbitrarily long time. I mean, arbitrarily many copies of the training data quantum states for arbitrarily long time. And the only reasonable case where that could happen is where you're preparing the states yourself, which in my language means you have classical data. Does that make sense?
I think previously said I kind of shouldn't care about this, but I'm not sure whether I do or not. So the whole premise of this is that you can choose a map phi which embeds this into a linear separation problem. And in this quantum case, and in practice, does this always work? Because if you don't have linear separation in the high dimensional space, this whole linear optimization approach doesn't work, right?
So the promise is this will be as good as it gets. If this is not good enough, you should not be happy. Whether as good as it gets is good enough or not will depend on how you design the feature map. I didn't say you shouldn't care about this. You should care super much about this. This is the thing on which everything hinges.
Yeah.
I told you I will not tell you.
Right. Yeah.
But super important, problem dependent, and super important.
Right. Okay. And for all applications, people care about this is always possible. You can always choose a row which.
No.
Oh, you can't. Okay.
Well, we don't know much about how to choose good rows. I'm not telling you. Not because...
Is like for what percent of application does this on-kernel method thing
0
work? Okay.
QML, and this extends to all QML.
Okay. No, that's good. Yeah.
So if I had a false article.
Sorry, wrong. For those where secretly the quantum kernel method is just a classical kernel method evaluated on quantum.
Yeah, sure.
So connected to what you said previously about evaluating it for all data. So in theory, if I had a quantum computer, that would be just like amazing. I could compute this and that write as sum of alpha i's with row xi's, right? And compile that as one observable, and then tomorrow I would come and just.
If you're that smart, yes.
Okay, yeah. My experiments are bad.
Yes. Option one, the variation approach, because it relates to this, appeared in parallel with the Naive error, because the idea is for some very generous noise models, your parameters could learn the noise,
Yeah.
which doesn't happen.
Yeah.
Cool. Any other questions? I think these are all very good questions. Feel encouraged to keep asking questions. Okay. Very good. So, UML is just kernels. This is very, very close to the title of reference 3. Yeah, I didn't tell you references 1 and 2. Not such a pedagogical presentation, but like references 1 and 2 talk about these things, and were among the first references to talk at the same time about the variational approach and the kernel approach, and even run it on hardware and not even compare, but just say, look, there are 2 things you could do in kernel. That was 2019. 2021, Maria Schul was like, are there really 2 things you could do? Or is there secretly only one? And now, for that, let's consider function families. Okay, I think I defined them still. So F sub rho is all linear models of rho. F sub rho var is a subset of all linear models of rho. In particular, is a subset of at most p dimensions. I'm talking about function families. You could ignore my function families and just think of the observables. Like this would be all Hermitian observables. This could be the set of all n thetas for all theta. And next to it, we have the set of quantum kernel methods, which is, so the F sub rho bar is this, F sub rho S is that. In principle, these are 2 different families of functions, which come from 2 different families of Hermitian matrices. It's not very useful to think about it, but to me, it's clear to think about it as this is an exponential dimensional object. We came up with 2 different ways of characterizing polynomial dimensional subsets of the same. And in principle, those things don't relate to each other. So in principle, they give rise to different things. Now, in the imagery of there's a training data, there's a learning task that we're trying to solve. We do the option 1 and the option 2, blah, blah. Eventually, we reach some solution to a given training problem. Like imagine I have 1 training task and I use that training task. I try to solve the same learning task with both options for a fixed quantum mixture. Okay, there's a learning task that's given to me. I look at it, and based on it, what I see, I decide on a feature map. Now I have decided on a feature map. I have a choice. Do I want to do the variational approach or the kernel approach? I don't make the choice. I try both just to see what happens. And it just so happens that these are the optimal things that the algorithms find. And we have a question.
Shouldn't one of the circle be inside?
No.
No, I mean the kernel method, the RKHS code.
Yes, this is not the RKHS. We'll get there. We'll get there. This figure is on this paper. On this paper. Like, I'm not pushing my private agenda, which I have. This is how Maria should run it. Okay, we have those things. Somehow, this is like, I think, figure 1 of this paper. And this brings the author to say, essentially, like, in a rational way. And the question is, what else did the author say for them to even get to talk about things this way? Like, how could it be that if these are independent sets that contain different functions, how can it be that someone claims they are the same thing? And this is where you go back to your linear optimization book, and you find something called the representative theorem, which is just putting in different words the things we already said. What the representative theorem says in some weird notation is that if you have this optimization problem, so you're looking for the optimal exponential dimensional linear separator captured by the training, like the empirical risk. This is the average of the error over the training data, plus something that accounts for that you don't want to have high norms for whatever reason. Then the best such linear separator is a kernel method. So we call this the empirical risk minimizer. The empirical risk minimizer is belongs to the family of the kernel method, and further is exactly the output of this linear optimization thing we did. So the linear optimization step for option 2 is not only good for option 2, is good over all linear models. And now I have some bullet points.
Sorry, what is F rho n? Because previously couldn't do F rho.
S, sorry. You're
Okay, yeah.
right. Yes, sometimes I forget this. So, optimal separator of training data is kernel, which means training error of variational is lower bounded by the training error of kernel. This is powerful. And it's powerful and easy because this is just rewriting what the linear optimization book told us. This is just good. It tells us if your goal in life is to find the best training error, like the best empirical risk, together with some normalization, which is very common in all of machine learning, then the best thing you can do is use a kernel method. And this is how somehow the bottom line of this paper is everything you should want is the kernel method. Right? So
But like this kind of assumes like noiseless case, no? Because we wouldn't compute the kernel exactly on a quantum computer, so then we wouldn't find our optimal. And then
sure, yeah. I mean, most of what I say assumes their noise doesn't exist. Because, yeah, some things break. This is some of the asterisks that I decided to leave out. Yeah, it's super important. Good. So, QMI is just kernels. QMI is not just kernels. This is reference 4. And the story is very, the height of the story is very, very simple. And it goes full cycle to what we said at the beginning. We want expected risk minimization. So kernels are empirical risk minimizers does not imply kernels are expected risk minimizers. And this is kind of subtle. It took a bit for us, the community, to see the implications of this. It's not that crazy a statement, but phrased in the way I phrased it is like what Maria Schultz tells us is relevant for the problem we can solve, which is important. But we should not forget the problem we want to solve. And from the point of view of the problem we want to solve, these guarantees don't mean nothing, but they also don't mean everything. So not everything you should ever want is kernel methods. And Sofian nicely provides a cool separation. I wrote down some notation, but it will not make a lot of sense, and it's not so relevant. But in that paper, number 4, Sofian and co-authors come up with a learning task, which is not too crazy. It's like learning partial parities. And they show that a very easy, silly variational machine learning model can solve the task perfectly with no problems, constant, everything great. And no quantum kernel method could solve it unless it is provided exponentially many training data. The proper statement is there is a function family contained in here, which has large distance to here, meaning there's at least always one element of the family that's very far away from the things you can reach.
And that's compatible with this Maria Schultz own kernel methods.
Yeah, because in this learning task, the kernel method would achieve good training error.
Yeah.
It's just guaranteed to achieve trivial test error and expected risk. So it solves the problem we can't solve perfectly. It solves the problem we want to solve as bad as it can.
I think Maria's technical is only valid when we think about that M. Observer M is some kind of universal set of observers.
Well, it's not true in general that you never want kernel methods. So I'm not making big statements. I'm just saying there are functions here somehow. Okay. I mean, this is very subtle. Maybe we can talk about it offline, but the statement is there exists a learning task in which variational QML succeeds with flying colors, and any kernel method, any linear-based approach, any kernel method, that is spectacular. That's the statement. And it's up to us to have implications of what does that mean for the big picture of QML. Okay, this is super important to me. It's like cool. Maybe it's not very important to you, but it allowed me to have like the funny story. And this is the end of the funny story. If you have any questions,
So you mentioned something that like unless the training data is exponential or something.
yes.
So like if the training data is big enough, then kernels are good. I'm not sure I quite.
The training, you can think of it as random variables. The training error is an unbiased estimator of the testing. if we have finite training data,
Right.
then there will be some square root n difference between the two. But the disagreement between the training error and the test error goes down as 1 over square root n.
Right. So in that sense,
So that means-
empirical converges to explain. Okay.
And this is independent of kernel methods. Whatever learning algorithm you have, if you have enough training data, you're guaranteed to converge, assuming things are smooth and stuff. But
Yeah.
they typically are. In kernel methods with exponential data, then you have optimality for the training error and guaranteed convergence to test error. But if you have that much data, you're out of the framework of supervised learning because you want to learn from a few examples.
Right.
So from polynomial examples.
Yeah.
Very good. Then, as I promised you, the last part is just I will write a bunch of papers that if you thought these things are cool and you will like more good things, I'll just give you some nice papers to read that now you can read quickly. Hopefully, with what I can put here, and then you have a nice list. But otherwise, I'm done with the content.
And also all the references are also in your lecture notes. So
Yes,
I guess we'll post them in Slack afterward.
yes. Yeah, you're right. Well, I guess I'll do it for completeness. Still ready.
No, sure.
Yes. Also, I have planned to type them out, but then I realized that there's really no punchline and not much content. So then I thought it was not a worthy endeavor. If anyone has super strong feelings that I should take it up, let me know and I'll do it. But I wasn't so sure. So there's this famous paper with a provable, robust, and rigorous quantum advantage in learning. It's this paper, and it's based on kernel methods. So now you can just go and read it. Those ones I already wrote. Then one of, you remember there used to be a time that I was depressed always talking about my kernels paper? My kernels paper was kind of an obscure thing that doesn't relate very well to what I presented today, but it's just a lot of fun. So now by reading the abstract, you can judge, you can understand exactly why it was fun, and you can judge whether that would be for you. Then there's been a recent re-rise of ambitious titles of saying, that's not what the title says, but like saying everything is X, Y, Z. And there was this paper published in a fancy machine learning conference. Where the honest title is everything is RFF. I will tell you what RFF means. I will not tell you what RFF means. But this is the setup for another paper from this house. This honest title is not everything is RFF. And then, like beyond kernels, like other things in the world, Sophia has another super nice paper that I would also recommend. Yes. Good. That's it.
Oh, then